Solidity supports some contract related primitives that need to be understood. The keyword this refers to the current contract, and it can be converted to an address type explicitly. And more importantly, there is a primitive known as SelfDestruct that Solidity supports. Recall that there's a SelfDestruct instruction in the EVM, which we talked about in the Ethereum module. This primitive is really a high-level wrapper on top of that instruction. It takes in a single argument, an address type specifying the recipient, and what this recipient signifies is that when this contract is destroyed or destructed by this primitive, all the funds, the ether balance in that destroyed contract, are sent to this recipient address when the execution ends. There are some specifics of self-destruct that need to be kept in mind from a security perspective. So let's take a look at that next. The recipient address that is specified in this primitive does not execute the receive function when it is triggered. Recall that contracts can specify a receive function that get triggered on ether transfers or under other conditions. In the context of self-destruct primitive, if the recipient address happens to be a contract and it specifies a receive function, that does not get triggered when self-destruct happens. This is critical because any logic that might be within that receive function might have been anticipated by the developer to be triggered anytime ether is received by that contract, but self-destruct is an exception to that logic. Also, the contract gets destroyed by self-destruct only at the end of the transaction that has triggered this flow. And what this means is that if there is any other logic after self-destruct that may revert for various reasons, then that revert undoes the destruction of the contract itself. So just because we see a self-destruct in the control flow does not mean that the contract gets destroyed, because logic after that might revert and really not result in the destruction of this contract. Solidity supports some primitives specific to the contract type. Type of X is the syntax for doing so, where X is that of a contract type. The primitives supported are a dot name that returns the name of the contract. Creation code and runtime primitives return the creation and runtime byte codes of that contract. These are interesting details that are best examined by writing a simple contract and looking at what these primitives return. There's also the interface ID primitive that returns the identifier for the interface specified. We'll take a look at the differences between interfaces and contracts later on, but these are primitives that are supported by Solidity specific to the contract or interface type. There are similar primitives supported for integer types. This again represented by type of X, where X happens to be an integer. Type of the integer .min returns the smallest value representable by the type T. And similarly, .max primitive returns the largest value that is representable by the type T. And what this means is, as an example, if we say type of uint 8.max, then it returns the maximum value representable by the unsigned integer of size 8 bits. And in this case, it happens to be 255, which is 2 power 8 minus 1. Let's now switch gears and look at the various types of control structures that are supported by Solidity. These are really fundamental to any programming language because there is a control flow to the sequence of instructions specified in the high-level language that get translated into machine code by the compiler. In the case of Solidity, the control structures supported are if, else, while, do, for, break, continue, and return. These are very similar to the ones found in really any of the programming languages. There are some differences in Solidity. Parentheses, for example, cannot be omitted for conditionals that some of the other languages support. However, curly braces can be omitted around single statement bodies for such conditionals. Also note that there is no type conversion from a non-Boolean to a Boolean type. As an example, if of 1, where we specify that integer 1 is not allowed in Solidity because 1 is not convertible to the Boolean true, which is supported by some of the other languages. So control structures play a critical role in the security analysis of smart contracts, whether you're doing a manual review or whether you're writing a tool to parse the Solidity smart contract. So these are some things to be understood really well because that's really how control flows, and any analysis really depends critically on making sure that the control flow is accurately followed and representative of what really happens at runtime. Solidity supports the concept of exceptions to a great extent. We touched upon this under error handling. And what this really means is that in Solidity, exceptions are used to handle errors, and these exceptions are state reverting, which means that an exception undoes or reverses all the changes made to the state of the smart contract in the context of the current transaction. The calls and all the subcalls that may be several levels deep, all the changes that they have affected to the contract state are reversed. And this also flags an error to the caller so that they can take appropriate action. So when exceptions happen within subcalls in that call hierarchy during runtime, they bubble up. And what this means is that exceptions are rethrown at the higher level calls automatically. There are some exceptions to this rule. There are some differences here in the context of the send primitive and the low-level function calls, the call, delegate call, and static call, which we talked about earlier. These primitives, send, call, delegate call, and static call, return a Boolean, true or false, as their first return value, instead of an exception bubbling up. This is an important distinction to be kept in mind when analyzing smart contracts, because the exception behavior is different for these primitives compared to the standard message calls. Exceptions that happen in external calls made during the contract execution can be caught with the try-catch statement. We'll look more into that in the next few slides. And these exceptions can contain data that is passed back to the caller. And this data consists of a function selector indicating which function the exception happened in, and also some other ABI encoded data that give more information about the exception. And Solidity supports two error signatures. We talked a bit about this, the error and panic. Error takes a string parameter, whereas panic takes an unsigned int parameter. Error is meant to be used for quote-unquote regular error conditions, such as input validation and so on. We talked about in the context of the require primitive, while the panic is used for errors that should not be present in bug-free code. So this is really the assert primitive situation where program invariants are being violated and panic is meant to be used there. Let's now revisit the concept of low-level calls and talk about a very specific peculiarity or counterintuitive aspect of these calls. As we first talked about these calls under the EVM instruction set, there is call, static call, and delegate call, each of them corresponding to the specific instruction that implements these calls. The counterintuitive aspect is that if these calls are made to contract accounts that do not exist for some reason, they still return true based on the design of the EVM. And this can have some serious side effects if the contract logic really assumes that the external call was successful and executed the logic that it expected it to execute because it got a value of true from these primitives. And the mitigation for this aspect of low-level calls is to check for contract existence before these calls are made and have the logic handle it appropriately if they do not exist. This has resulted in some serious security vulnerabilities being reported in various high-profile smart contract projects. So something to be kept in mind when analyzing the security of smart contracts that use these low-level calls. Let's revisit the concept of the assert primitive again. As we talked about, assert is really meant to be used for the program invariants that should never be violated within the smart contract if it does not have bugs as intended by the developer. These asserts result in the panic errors that take the UN256 type. To reiterate, they should really be used for internal errors for checking invariants. Normal code, bug-free code should never cause panic. And comparing it to the require primitive, assert should only be used again for program invariants and not for checking things like invalid external inputs or invalid interactions with external dependencies. Diving deeper a bit into what the panic error is. Panic exception is generated in various situations in Solidity, and the error code supplied with the error data indicates the kind of panic. There are many of these error codes. Some of them are 0x01, which indicates that assert has an argument that evaluated to false. 0x11, that is the error code that corresponds to an overflow or underflow that happens in arithmetic. Then there is a divide or modulus by 0, there is popping of an empty array, and so on and so forth. And finally, there is the 0x32, which is the out of bounds access for an array. So there are numerous error codes related to panic, and I would encourage you to take a look at them to understand what these codes are that you might encounter with these panic situations. Let's now revisit the require primitive. The require primitive in Solidity either creates an error of type error string or an error without any error data. And this should really be used to detect invalid conditions during runtime that cannot be prevented at compile time. This includes input validation, which is really a fundamental pillar of programming language security. Inputs at runtime that are obtained from users interacting with the contracts should be validated to make sure they are within the thresholds of what is acceptable with the smart contract logic. There are some sanity checks on those values. And require is also to be used for checking the return values from calls that are made to external contracts. So any type of external interaction, be it inputs from users or return values from external contract calls, are really what require is meant to be used with. And require takes in an optional message string that is output when the condition fails. Let's take a look at some of the situations wherein that error string exception is generated. As we just discussed, this is generated when the require executes and its argument evaluates to false. But the error string is also generated in other situations, such as an external call made to a contract that contains no code, or if the contract receives ether via a public function without the payable modifier, or if the contract receives ether via a public getter function. Let's revisit the concept of the revert primitive in Solidity. There are two ways to explicitly trigger a revert in Solidity. They're using the revert custom error primitive or the revert function that takes in an optional string parameter. In both these cases, the execution is aborted and all the state changes made as part of the transaction are reverted or reversed. And this distinction between custom error and the string is interesting from an optimization perspective and from a use case perspective. Let's now dive into the try-catch primitives that are fundamental error handling or exception handling primitives supported by Solidity. The syntax looks like this. There are the try and catch keywords coupled with the expression that contains an external function call or a creation of a contract itself. These are coupled with code blocks corresponding to the success blocks or the catch blocks. These are really code segments within the curly bracket shown here. Which block gets executed depends on whether there was a failure or not in that external call within that expression. So if there were no errors, then the success block gets executed. This is the block that immediately follows the try expression in the syntax shown here. But if there was an error in that external call, then the catch block or one of the catch blocks gets executed. Which catch block gets executed depends on the error type, and there are multiple of them. So let's take a look at what those are next. Solidity supports different kinds of catch blocks depending on the error type. There is a catch block that supports an error string. This is executed if the error was caused by revert with a reason string or require where the condition evaluated to false. Then there is a catch kind that supports the panic error code that we talked about. Now if this error was caused by a panic, failing assert, division by zero, or numerous other things like out-of-bound array accesses, arithmetic underflow, overflow, this is the catch block that will be run. Then there is finally a catch that specifies the low-level data. As shown here, this is the one that gets executed if the error signature does not match any other clause shown above, or if there was an error while decoding the error message itself, or if no error data was provided with that exception. And this variable that is declared, the low-level data, gives us access to the error data in that case. And finally, if the developer is not really interested in the type of error data, one can simply use catch as is with just a catch block. And these give various options to deal with different types of exceptions that might come from the external call that is used within the try-catch primitive. Let's recap the different state changes that are effected under the different conditions that one might encounter with the try-catch primitive. As we just discussed, there are concepts of the success block that gets executed when there are no exceptions in that external call. And there are also error blocks that correspond to the different catch blocks which get executed when there are exceptions encountered in that external call. So if execution reaches the success block, it means that there were no exceptions in that external call, and all the state changes that are done in the context of the external call are committed to the state of the contract. But if execution reaches one of the catch or error blocks, then it means that the state changes in that external call context have been reverted because of the exception. There could also be a context where the try-catch statement itself reverts for reasons of decoding or low-level failures. These failures of the external call made in the context of the try-catch primitive could happen for a variety of reasons, and one cannot always assume that the error message is coming directly from the contract that was called in that external call, because the error could happen deeper down in the call chain resulting from that call, and it was forwarded to the point where it was received. This could also be due to an out of gas or OOG situation, in which case the caller still has a bit of gas to deal with that exception because not all of it is forwarded to the callee. Let's recognize that a lot of these concepts, specifically related to the error handling and exception handling, is hard to explain verbally in the context of this presentation, and it is very likely, very understandable that it is harder to visualize a lot of these and understand it just by listening to a lecture. So I would strongly encourage the listeners to look at some illustrative examples given in the Solidity documentation for all these situations of exception handling, and even better, to code up small contracts, illustrative examples, if you will, that trigger these exceptions, the different kinds, the different error strings and reverts, the panic codes that we have talked about, to really understand how all these work and fit within the context of exception handling. Let's now switch gears quite a bit and talk about a topic that is more subjective than all the things we have discussed so far. So all the aspects of the various basics of Solidity, the syntactic aspects, the semantic aspects, are really rules that are enforced in Solidity grammar. Programming style, on the other hand, is coding convention. And these can be different, these are different across different developers. Different styles are adopted based on what the developer is comfortable with, based on what they believe is an optimal way of programming. But fundamentally, the programming style is about consistency. And the reason for this is because programming style affects the readability of the code and maintainability of the code. So when anyone other than the developer looks at the code to evaluate the security, to audit it, or to make fixes or extend those smart contracts, the consistency of the programming style becomes important. If different styles are used within the same function, within the same module, or within the same project, because of the same developer not being consistent, or because multiple developers are involved in that project and they all have different styles, then this significantly affects the readability aspect and the maintainability aspect, both of which have a significant impact on the security life cycle of the code. There are two main categories of programming style, that of code layout and that of naming. Let's talk more about each of these categories in the remaining slides. Code layout refers to the physical layout of the various programming elements within a source code file. And there are many programming style aspects related to code layout. Those related to indentation, where the best practice in Solidity is to recommend 4 spaces per indentation level and to prefer spaces over tabs and to definitely not mix them. There are also style guidelines with respect to blank lines used to surround declarations with the max line length that's recommended to be 79 or 99 characters for best readability. There are also recommendations for wrapping lines for the encoding used in the source files and for keeping the import statements at the top of the file and not anywhere else. And finally, the ordering of the functions within the contracts, where the recommendation is to have the constructor as the first in that order, followed by functions of differing visibilities, grouping all the external functions first, followed by public functions, and then internal, and then private functions. There are some more code layout programming style guidelines specific to the use of white space within expressions, curly brackets and spaces in control structures, function declarations, mappings, and variable declarations. Strings are recommended to be used with double quotes instead of single quotes. Operators and spaces have some guidelines as well. And finally, the ordering of different program elements within a Solidity file also have a guideline, which is to have the pragma declaratives all the way at the top, followed by the import directives, and then the contract library or interface definition itself. Within each of the contracts, libraries, or interfaces, the guideline suggests using the types first, followed by declarations of state variables, then events, and finally all the various functions. The next aspect of programming style is naming convention. This refers to the names that are given to various variables, events, contracts, libraries, and all the different program elements used within smart contracts. There are different types of names: lowercase names, lowercase with underscores, all uppercase, uppercase with underscores, capitalized words, mixed case, capitalized words with underscores, and so on. All these different types are recommended to be used for different program elements. And as a general rule, the guideline is to avoid letters that can be confused with different numerals, like the lowercase letter L or the uppercase letter O, uppercase letter I, that could be confused with 0 and 1 numerals. Contract and libraries should be named with cap word style. They should also match their file names. And if a contract file includes multiple contracts and libraries, then the file name should match the core contract, or what is considered as a core contract for that file by the developer. Structs should be named using the cap word style again, as shown here. Events should be named using cap word style again. Functions should be named using mixed case. And this is something that you'll encounter often within contracts. Developers are sometimes consistent with these namings, sometimes they're mixed up because of multiple developers, or the style just not being consistent, or being confused with that of some external libraries. Again, all these aspects affect the readability and maintainability. They do not have any impact on the syntax or the semantics of the contract itself. The bytecode is just the same, but it has an effect to a certain extent on the security audit aspect. When you look at this code and when the naming convention is different or not consistent, then it could lead to some assumptions being made on these variables being the same ones or different ones. So something to be kept in mind and paid attention to. Some more naming conventions with respect to the other program elements. Function argument should be in mixed case, local state variables again in mixed case. Constants, however, should be with all capital letters and underscores separating the multiple words if they are present. Modifiers in mixed case, enums in cap word style, and finally, one should avoid naming collisions where the desired names of variables or functions collides with that of a built-in within Solidity or any other reserved name. So those should be resolved using single trailing underscores in those names. And to reiterate, these programming style aspects are subjective in nature. Different developers, different teams might have different philosophies as to what works best for them. The key really is consistency within the functions, modules, or contracts or projects. And this affects readability, maintainability, which is a critical aspect of security, specifically with respect to smart contract audits. So this brings us to the end of this module on Solidity Basics 101, where we have touched upon 101 basic concepts related to Solidity, and you will encounter all of these when you read smart contracts. And like I mentioned in the beginning, the expectation here is to understand the breadth of these concepts and time permitting and depending on your interest, take a deeper look at the Solidity documentation, which is fantastic, has many illustrative examples. There are many other courses or articles written about each of these concepts, such as syntactic styles, control structures, some of the security impacting primitives, such as SelfDestruct, asserts, requires, exception handling. A lot of these are really deep in the number of nuances that they have, and we certainly have not gone into the depth of any one of these aspects. The goal here is to give you an idea of all these aspects that are relevant to Solidity and covered in the Solidity documentation, so that you have a working knowledge of what these concepts mean, a high level understanding, and that'll help you to take a deeper look when you write your own contracts or when you read some of the complex contracts that are there in many of the applications in this space. So with that, we come to an end of this module. Hope you have a better understanding of the basics of Solidity if you weren't already familiar.